Okay, guys, let's go ahead and get going for today. Today's plan is to cover the Module 6, Chapter 6, Network Address Translation. And the assigned lab is Lab 6.8.2. And after I cover the PowerPoint slideshow, I'll briefly open up Packet Tracer and show you something a little different today. Maybe I had a crazy idea that maybe you might want to do the labs with the actual 4000 series routers that the labs are written for, so that the G000 matches instead of G01 that you have to translate for. So let's see how that works out. So the PowerPoint slideshow presentation for today. Is going to be this Module 6 Network Address Translation module. Oh, I forgot to load the PowerPoint. I got to load the PowerPoint, guys. Hang on just a second, I'll do that. It's loading, it's converting, we're walking, we're waiting. It'll be ready in just a second here. So as it loads, all home routers do essentially two functions. They do the DHCP function, and they do the NAT function, Network Address Translation function. Okay, here it is. So network address translation for IP version 4. Why not IP version 6? Well, IP version 6 got like a million, quadrillion, zillion Google addresses. We don't need network address translation for that. So network address translation was something they came up with in the mid-90s because they were starting to run out of the IP version 4 addresses. So we'll look at some we'll look at some entries here. We'll look at some issues here. So inside addresses at home, you use the C. Almost universally, 99% of all home routers will use the inside private address of 192.168.1.1 maybe for the home router. And your PC workstations are usually starting with 1.100. Most home routers do allow you to go in and change that default. If you want to use the 10. Network address instead, you can do that. But out of the box, that's what they normally use. So everyone's got 192.168.1.1. That seems like a bunch of duplicate IP addresses. But they'll be translated from inside your home network to an outside global unique address sent to you by your ISP. And one address works just fine with that. You don't need as many as you have devices. So these are the RFC 1918 spec was the specification they came up with, the request for comment specification of these private reserved inside addresses. The 10. For the Class A, the 172.16 for the Class B, the 192.168 for Class C. These addresses are not allowed to exist on the public internet. All internet service providers filter them out so they don't show up. So that means that someone tried to spoof an IP on the internet to be your same inside address and break into your business or corporation, it would be filtered, it would be dropped. They have to use some other method of getting it there. That's not going to work. So private IP version 4 addresses can't be routed over the internet. They're only for use inside your home, inside your company, inside your organization, inside your corporation. So this means that if I allow these addresses to flow out unchanged into the internet, they would be dropped. They wouldn't be transmitted. So we have to use a network address translation code to change these private addresses to public addresses so that they exist on the internet. And then when you log onto a web server on the internet, when that packet arrives back at your home network or your business network, we need to retranslate that public address to your private inside address so you will be able to see it and it'll go through your interior devices. So the reason for this was in the mid-90s, we started running out of these IP version 4 addresses. And all the routers were classful. They didn't allow variable length subnet masking. They didn't allow classless interdomain routing. And these were $1 million hardware routers that could not be replaced soon because they had not been depreciated yet. So the software guys said, we'll just write the software. We'll rewrite the software code. We'll rewrite the iOS to allow variable length subnet masking in classes interdomain routing, and that'll act as a band-aid to go to the outside world. And another thing they came up with was network advanced translation, so that, for example, Tarrant County Junior College, as it was back in the late 1999 to 2000, it used one class address for all our 100,000 students and 4,000 employees. So we were able to use the network address translation feature to translate our private inside addresses, the 10-dot type networks that we use on all our wireline plugged-in Ethernet devices like desktop PCs, the 172.16 range that we use for our Wi-Fi access points, to be translated to the outside world. Well, right after 2000, we got a Class A address, and we changed internet service providers. So it still works just fine either way. You really don't need a bunch of addresses to go to the outside world. So this way, private inside addresses, what we're going to call private IP addresses, private inside addresses, will be translated into global inside addresses that appear in the outside world. So your home router is at the border of your network. In a business, that router that typically connects to an internet provider would do the NAT function. So any packet that exists on the inside network that has a source address of, in this case of this yellow diagram, 192.168.something, when it hits the NAT router, he'll translate that to the outside address. So you can talk globally to those other devices, and they think you're a globally valid address and not an inside address that should be dropped. Okay, so here's an example. You're on an inside network and you have 192.168.10.10 as your host address. This could be a home computer machine. This could be on a network for a small business. So PC sends a packet to the web server. He's going to that web server 209.165.201.1 that looks like a valid globally unique IP address. Warning, Will Robinson, the address of 209.165 in the range of globally unique addresses, but it's address that's reserved for training and documentation. It's not a class A, B, or C inside private address. So it'll survive the NAT test and go to the outside world through ISPs. So R2 is going to receive the packet. R1 was our employee's desktop machine's default gateway. It goes to R2. And R2 is going to do the NAT function. He's going to take that inside global address of 192.168.10.10 and translate that to the address that was assigned to us by the internet service provider. 209.165.200.226, for example, in this case. Then R2 will send that translated packet to the destination. The cloud router and the server symbol represents the arbitrary web server we're trying to get to on the internet to see web stuff. So far as the server is concerned, you don't have the 192.168 address anymore. You have that 209.165 translated address. You've been translated to a global unique, perfectly valid IP address that's allowed to exist on the internet. So that's sent to the server. He responds. He thinks your destination address when he sends the packet back is that 209.165 address. And then when the R2 router receives it back, he started a table. When your original packet got translated, he started a table. If you're at home, your home router does this. He creates a little table in his RAM memory, and it says, 192.168.10.10. I had to translate that to 209.165.201.1. And when the answer comes back, he matches that up with the first part of the table, and he'll retranslate that address that the server thought you were back into the 192.168.10.10. The destination address of that packet coming from the real-world internet must be changed back to your inside address, or your inside network won't recognize it, and you won't be able to route it. So the packet gets forwarded back towards PC1, and the PC1 user's web browser now sees that page that he clicked on and wanted to see. So this process is transparent to the users, and it works real well with web applications. Okay, so definition here, inside address. That was the 192.168 type address that was inside of your corporation or inside of your home, probably assigned to that workstation by the DHCP process. Outside address is the address of the destination device. For example, the Microsoft web server, or the Cisco Network and Academy web server. The local address is any address that appears on the inside portion of the network. So at home, it's 192.168. At Tarrant County College, it's 10 dot something. In the classroom, we're 10.144 dot something. And the global address is the address that appears on the outside portion of the network. Because ISPs, if they encounter any A, B, or C 10.172.192.168, they're going to drop it like a hot potato. So the inside local address is the address seen from inside the network. At home, 192.168.100 is probably your first PC. Your default gateway of your home router is probably 192.168.1.1. Inside larger companies, it may be the 172.16 or it may be the 10 dot, like we use inside the college network. The inside global address is the address that's been translated. I have to change my 192.168 to that 209.165 address that's allowed to propagate through the internet before it leaves my gateway router or my border router that connects me to my ISP. Otherwise, it's going to be dropped. The outside global address is the address is seen from the outside network. And then the outside local address is the address is seen from the inside network. Not very commonly used. Don't worry about this. Okay, now let's just have a scenario here. And let's say that you went to Southwestern Bell or AT&T and you were getting their commercial DSL service that's designed for businesses. They typically give you 6 static addresses with that low-cost package for about $200 a month. And you're going to use the static addresses for your web server that people come to the outside world and see your products. And you're going to use another one of those static addresses for your mail server. And the other 4 addresses you're going to use for your employees that work inside the company. Those would be addresses, globally unique, perfectly valid internet addresses that your employees could have their packets translated to get to the outside world. Most companies are going to use a combination of static NAT and something later we're going to see in just a second called dynamic NAT. NAT is a forever one-to-one relationship between a private inside address and an outside globally unique address. In the example of this diagram, we see the server at the top on the left inside yellow rectangle is server 1, and that has an address that must maintain. We can't use dynamic NAT here because it would get a different address every time. We have to have a static one-to-one permanent relationship of whatever that inside address was on that server. It's 192.168.10.10. So that when it gets translated to the outside address, one of the 6 addresses we got from the telephone company, it will always be that same exact IP address. So the DNS servers on the internet will have an entry for mywonderfulcompany.com web server, www.mycompany.com. And it will always be that 209.165.200.226 address that's been statically mapped to that particular inside address. And we might map another address. For example, we might map our inside 10.11 as a mail server, and it would be permanently mapped to 227. We get these 6 addresses that we can use. You home customers, now this wouldn't work with you because you've got cable or DSL service, and you never know what one IP address you're going to get from the outside world. So you can't really. Now there are some techniques I hear that the gamers use, dynamic DNS, that somehow keeps track of your changing address and allow on the outside world so you can shoot down their F-15s and do stuff like that. But in the business world, we have to have a permanent static mapping to make that work properly. Dynamic NAT is what you're using at home. Dynamic NAT, all we need is one outside perfectly valid internet address, a globally unique address, not 10, not 172, not 192.168. And it doesn't matter what address it is. Your home router or your business router is going to translate all the inside devices to that one outside device. So dynamic NAT is just going to give you an address from a pool of addresses. There's other addresses available to use. This just requires that we have enough public addresses for our total number of inside employees. One address is fine for home users. You just have, how many do you need? A couple dozen at the most. Well, technically it should be 65,000 different possible addresses, but really 4,000 or 5,000 is more like it. So if you had 10,000 employees, you might need 2 static addresses from the outside world to make this work properly. So port address translation is the feature that makes this work. In static one-to-one mapping, I didn't have to monkey with the port numbers. I just changed your inside address to the outside address. And the destination packet came back, I changed it back to your statically mapped inside address. But when we do dynamic mapping to multiple inside clients, we need to somehow keep track of this. So we have 65,000 port numbers, we can do that. So with port address translation, NAT overload, what we're going to do is map a single public IP address that our ISP has given us to multiple different inside clients. And we're going to do some port address monkey business to make sure that when we take that 192.168.10 or 10.10 dot address from the inside network, we'll make sure we only have one outside address to work with. As long as we give them global port numbers, unique port numbers, it's going to work properly. Think of it as if you had if you just had one single PC, it's certainly possible to have multiple applications running at the same time. You could have a web browser and you could print to the printer. You can even have a copy of Netscape Navigator and a copy of Internet Explorer and a copy of Mozilla, all these browsers running at the same time. They would have different port numbers so that when the answers came back from the 3 web servers that each of these 3 browsers were connected to, your PC would have no problem distinguishing the 3 and mapping out the proper results for each individual web page. It's not going to commingle one web with another and mix it up on that. So instead of one machine with multiple sessions in it, we're just using multiple machines with multiple sessions in. And since we have 65,000 different port numbers, we can do this with a great number of machines, and it works okay. So this makes sure there's a different TCP port number for each session on the internet. So port address translation will attempt to preserve the original source port. Now, remember from your TCP chapter of Network Fundamentals, only servers are allowed to source information on the low-numbered port numbers, like port 80 for web or port 25 for email. Client machines are not servers. Normally, we don't install a web server application like Apache on an employee machine. We normally put that on a server in the server rack in the data center. So Microsoft machines typically would automatically generate a port number above 1,000. If 2 of them happen to make up exactly the same port number, the port address translation code will change one of them so there's no conflict. So he'll just move it to the next address. So in the case of these PCs, if they all just, for some weird reason, it was a full moon, and they both came up with the port number 1444, and all 3 of them are going to Network Academy, he wouldn't be able to tell them apart from each other if they had the same port number. So the port address translation code will let the first one stay 1444. He'll slightly adjust the second one to 1445. He'll slightly adjust the third one to 1446, so that when they arrive at that web server, he'll be able to distinguish between them. And more importantly, when the answers come back, the proper web page that you clicked on comes back to that device. This will continue until there's no more IP addresses available or no more ports available. And since there's thousands of them, for a home user, this is simply no problem. So NAT only modifies the IP address. The port numbers are preserved. It's a one-to-one mapping. This is not used for home. This is used in a business where I need to have one-to-one mapping for, example, at Tarrant County College, we have to have a one-to-one mapping for the Web Advisor server. We have to have a one-to-one mapping for the tccd.edu homepage. We have to have a one-to-one mapping for the MyTCC Blackboard page. Port address translation is from client machines that are going to webs on the outside world. It doesn't matter what the exact IP address is. It doesn't matter what the exact port number is. So one inside global address can be mapped to many inside local addresses. And we're simply going to do the monkey business with the port numbers to make sure that there's no conflicts there. Okay, some packets don't have a layer 4 segment. For example, Internet Control Message Protocol, echo request and echo reply are 2 of the things used by that. PAT handles these things separately by using a unique query ID number. So beyond the echo request and echo reply for pings to work, there's some other stuff that goes beyond that goes beyond the CCNA, so we shouldn't have to worry about that. Oh, by the way, speaking of ping, many companies filter ping anyway coming in and out of their networks, because what's the first step of a hacker to try to get into your network? He's going to try to ping all your available IP addresses, which he's got from the IANA name and number 30 people, to try to find out what you got that responds to a ping. Then if he finds the pings that answers, he's going to try to do a port mapping scan on them, like Nmap, and then try to define your server so he can get the good stuff. Okay, many benefits. The main reason we came up with is the first dot here. The first bullet point is it allows us to conserve our precious dwindling stock of IP version 4 addresses as a workaround until everybody can go over to IP version 6. So they started this about in the mid-90s. We still have a very slow adoption of IP version 6, only about maybe a quarter of companies are using it. But eventually, over the next 10 years, we'll move over to IP version 6 and get rid of IP version 4. This conserves addresses, gives us flexibility of connections. This allows our internal network addresses to remain consistent. Example, Tarrant County College recently changed internet service providers. We were using AT&T. Now we're using a different company based out of Monroe, Louisiana. I forget their name. Normally, if you changed ISPs and you were not using inside private addresses, you would have to change the IP addresses of all inside Tarrant County College machines. Well, 100,000 students, 4,000 employees, that would be a big job. But we're using private inside addressing. We just changed our NAT code on our routers, a few routers. We didn't have to change the addresses of all the internal machines. It was transparent to them. So we can change to a new public addressing scheme, and it doesn't affect our inside machines. We just have to go to the NAT router at the end of the network and change the NAT code on that to do it. It can do, as a security feature, it can hide our IP version 4 addresses from outside users that might try to scan us. So you can't, for example, from the outside world, my teacher machine is 10.144.100. something. You can't ping that from the outside world. It would be translated and it wouldn't work. We don't allow things into our company. There is latency. It's got to change the addresses of the packets when they're propagated out. And then it's got to change the addresses back so it'll work when the answer comes back to our internal company. So it increases forwarding delays. There's a slight delay. Oh, it's 1,000th of a second. It's no big deal. End-to-end addressing is lost. We have the outside people world can't see my real address. It's also possible to that web server I'm connecting with, it is in a corporation and it's privately addressed inside that corporation, and I'm only seeing the NATed address that they put to the outside world. So we lose our ability to trace end-to-end IP version 4. This might mess up, for example, a traceroute command if you wanted to see everything. If you're using a tunneling protocol such as IPsec, IP security, this complicates this. Services that require you to start a connection from the outside network, stateless protocols like UDP, it can give them a problem as well. So everybody's working from home now. All these programs that you can put on your PC where you can dial into your company PC from home, they have to work around all these problems because you're supposed to initiate the connection from within the company, receive the answer back. You're sort of going against the tide when you try to come in from home, go through your company firewall and initiate a connection with an inside device. So they have to use some tricky web HTTP stuff to do this. Okay, let's look at static NAT. One-to-one mapping. This is what I'm going to do for the Web Advisor server, maybe, or the MyTCC Blackboard server, or our public website, tccd.edu. A one-to-one mapping between that inside device and our college, it's 10 dot something. We use the 10 dot addresses for our inside Ethernet attached machines. So static NAT is going to allow communication with outside world devices. Like a student wants to log into WebAdvisor and see which courses, oh, the fall 2020 courses are online now. You can't register for them yet, but you can go look at them and see when they are. So an internal web server could be mapped to a specific address that's available to the outside world. So we used to map, well, when we were AT&T, we used to map to 64 dot something. We've changed now. I'm not sure what the address is. So we went to our new ISP. So what we want to do is go to our router and create a static mapping. In this particular case, the first orange line, it says IP NAT inside source static 192.168.10.254. Now we're actually 10 dot something, but let's pretend that's the web advisor server that you were trying to connect to see the classes for fall 2020. That has to be mapped to an outside address to survive on the public internet. And so that when you type webadvisor.tccd.edu, the DNS service of the internet would see, well, that's the public address that we exist on the real world with. So the DNS would say wa.tccd.edu is actually 209.165.201.5, and you would be able to connect to it. Okay, there's our relationship between the inside private address and the outside global unique, the inside global address, so-called, the outside global address that everybody else sees. Now what we're going to do is go to our serial ports, and serial port 010, that's the serial port that goes to our inside network. Of course, we would apply an IP address to our inside network, 192.168.1.2, and Tarrant County College would actually be a 10 dot address. And then we're going to map or mark that inside port, 0010, as the inside the company, the trusted inside network with IP NAT inside. Then we're going to mark our outside port, 0011 goes to our ISP, and they've assigned us the address of 209.165.200.1, and we'll mark that as the outside port. So you have to tell the iOS which one is inside and which one is outside. So several years ago, typically the serial port that went to your ISP would be marked as IP NAT outside, and the Ethernet port that went to your inside corporate network would be marked as the inside port. These days, serial ports are sort of falling out of favor. Instead of using T1 lines or things of that nature, most people are using Ethernet handoff. Like at home, you have an Ethernet handoff for your cable modem or your DSL modem. So typically, one Ethernet port would go to the inside network, and the other Ethernet port would go through that Ethernet handoff box, you know, multi-protocol label service or Metropolitan Ethernet or something like that, to your ISP carrier, and you would mark the appropriate port as being inside and outside, so he knows what code to translate. So you know that NAT code you typed in, he knows which port to associate with the inside 192 address and which port to associate with the outside address. So here's what happens here. Let's take a look at this. Number one, the client sends a packet to a web server. It goes to his default gateway router, R2. R2 takes that and he looks in his NAT code and says, oh, I have to translate that 192.168.10.254 address to the outside world. Okay, I'm going backwards here. Let me start again. Number one, the client machine from the outside world creates a packet, and it's 209.165.200.254 is his source address, and the destination address in that number one yellow envelope is 209.165.201.5, and that hits the router, and the router changes it to the globally, that router propagates through the router to R2, which is the default gateway router for the web server you're trying to connect to. R2 receives a packet from the client, and he translates that with his NAT table. He's going to translate that inside global address to that inside global address, the public address that's allowed to exist on the internet. I'm on number 3 now. That needs to be translated to the 192.168 address that's on the inside of the machine. So the NAT table looks in this table. He does that function. The web server then receives the packet because that's what his address is. He's got an inside private address. He doesn't have a globally unique IP address. He then sends it back to that globally unique address. It goes back to the router. His source address of 192.168 has to be translated back to a source address of 209.165, or the ISP would drop it. And then you, the client machine on the far right, then receive a packet, and it matches the web request that you sent, and you get that web page on your browser. So sounds complicated, but very quickly done by in thousandth of a second or less by these NAT routers that handle this function. Your home routers, which cost $20, have no problem doing this with very minimal processing power. On a Cisco iOS device on a router, to verify this operation, we're going to type show IP NAT translations. So when we type this command, first of all, we see the global mapping we did with that static IP static NAT command. And then after a couple of transactions has occurred, we see the actual addresses of the outside server that the guy went out and connected to, and they appear in the table. This used to be a optional extra credit thing I would do in the skills exam for this particular semester, but I'm cutting you guys a break this time. No one has to do any skills exam this semester. You must, however, perform this lab, and you'll do it in that. Okay, show IP NAT statistics shows information about, how many translations have taken place, how many things didn't match and were classified as misses. So in this case, we had 4 valid transactions and 1 transaction that did not match up and it was dropped. If you want to type clear IP NAT statistics before testing, you'll clear these counters back to 0, and then you can run your test and make sure that your particular thing is working. Okay, now dynamic NAT. Most companies are going to use a combination of a few static NAT mappings to their inside servers, like we would require at least 3 for the Web Advisor and for the MyTCC Blackboard and for the tccd.edu web server. And then we're going to use dynamic mapping for our thousands of employees. So dynamic mapping is going to map inside local addresses to what he calls inside global address. These are the global unique addresses that exist in the outside world. So in that case of that smaller company that bought the package of 6 static IP addresses, and he had maybe 2 servers, he has 4 addresses left that he can give to the NAT pool for the dynamic NAT. Now, if we don't use the NAT overload command, we're stuck with just 4 users at a time. So normally we're going to type in the command and use the keyword overload to say, use port address translation to make sure that more than 4 of my employees can get out to the outside world, because you might have more than 4 employees. So step 1, we're going to define the pool of addresses that will be used in translation. This is the first line, IP NAT pool, and he's made up a NAT pool keyword and he's put it in all caps. Whenever you create a NAT pool or a DHCP pool, it's considered good practice to put it in all capital letters because it makes it sort of pop out in the listing. It's actually case insensitive. You can do anything you want to, but just put it in all caps. That's the standard convention. And then he puts his pool of addresses that's used here. In this case, he's putting addresses from 209.165.200.226 through 240. So that kind of looks like a /28 type address with 14 usable IP addresses. And then the net mask is 255.255.255.224. And then you have to create an access list to say which users on the inside of the company will be allowed to be translated to an outside address and get connectivity with the internet. So in this case, the companies, all the employees get it. Everybody in the company is 192.168.something. So access list 1 permits that, a standard access control list. Now, what if it was a public school environment? We might say only 192.168.1.0 can get out, and put the administrators and the high school students on that network. And then we might put the kids under 13 on the 2.0 network, and they would not be allowed to get out to the internet because that's a wholly dangerous place and they can't sign up for Facebook. And we have some laws that we have to comply with. Children under 13, we have to watch out for them. When I create these YouTubes and post them on the recorded videos, YouTube asks me, does this have kids in it? Because they have to be very careful about kids under 13. The third statement, IP NAT inside source list 1, those addresses that are allowed to go to the outside, bind that to the NAT pool list and allow those translations to take place. So these 3 lines of codes will make this happen. Okay, now we're going to go to step 4 and 5, identify which interfaces are inside and which interfaces are outside. We did this before with static NAT. So we have our first 3 lines from the last slide. And then we need to map the serial 010 as our inside port and our serial 011 as our outside port. So 10, 20 years ago, probably the inside port would have been Ethernet and the outside port would have been serial. These days, probably both the inside and outside ports would be Ethernet based. In the lab you guys do, it's going to be all Ethernet based. You won't be using any serial ports. So now we've created our 3 lines of mapping change the addresses and do the NAT function. And then we told the router which is the inside trusted network and what's the outside untrusted network. And you can go ahead and do the whole thing. So 2 PCs, now they're on the left side where they belong. PC1 and PC2 are both sending something to outside servers. So PC1 and PC2 both send packets to the default gateway router R1. The router receives a packet in PC1, checks to see the access control list is in a allowed address. Well, in this case, it was. It was 192.168.anything. He selects an available global address and creates a translation entry in the NAT table. Then R2 is going to have to translate that inside local source address of 192.168. That'll never live on the internet. It's got to be translated to the globally unique, perfectly valid internet address of 209.165, in this case 200.226. And then the second PC gets 209.165.200.227. We didn't use the overload keyword. We're limited to the number of available outside addresses. If we have a bunch of clients and limited outside addresses, we're going to have to put in that overload keyword statement to make that take place. So the server now receives the request from PC1. He thinks he's 209.165.200.226. He receives the request from the second PC2. He thinks he's 209.165.200.227. When both these packets flow back to the company, the NAT router will retranslate those 209 net addresses, which don't match my actual inside address. It's just 192.168. It's RFC 1918 Class C private address. And then the inside PC1s and PC2s will receive their web browser requests, and they'll be able to view them. Okay, we can show IP NAT translations in this case and see the translations that have taken place between the 228 and 229, the 10 dot and the 10.10 and 10.11 workstation. See that take place. There's also a verbose that you can see, for example, when it started, when it was used. Okay, we can verify this by using these commands like show IP NAT translation. Again, if you want to clear it out and just not see thousands of entries in your company, you can type clear IP NAT translation, the start asterisk character, and that'll clear it out. And then when you do show IP NAT translations right away, you'll get just the most recent entries. You can do your ping test or whatever and make sure it works properly. Show IP NAT statistics will show you what's happened here with your dynamic NAT table. And he's omitted some output here. Show running configuration. I just type show running config and the pipeline character. Include NAT means skip to the NAT. Don't see the whole 3 or 4 pages of stuff. And you can see your code that was put in effect for this. Okay, you're at home and you only have one global unique IP address. Or you're like Tarrant County Junior College used to be around 2000, where we had a Class C address and we didn't have a bunch of addresses for a one-to-one relationship to our inside people. Hey, it costs a lot of money to buy a bank of 4,000 IP addresses from the outside world. So we're going to do code very similar to what we did before. The difference is the orange word overload. That's going to tell port address translation to use a single IP address to the outside world, like you got at home, and have multiple addresses. Multiple inside hosts will work with that. Instead of just doing the layer 3 IP address translation between inside and outside addresses, this is going to also go to the layer 4 port numbers, modifying port numbers if required, so that unique port numbers are associated with each individual unique inside machine in the company or at home. And then you'll be able to get your response, and you won't be able to get God knows what your teenager's looking at. You don't want to see anything. So this keeps everything appropriately separated. Oh, it's possible for an ISP to allocate more than one public IP address to an organization. So in this case, similar to what we did before with dynamic NAT, we had a range of addresses from 209.165.200 to 226 through 240. We could use those, how many is that, 14 addresses? And we can use those 14 addresses and spread those out and have our thousands of employees use that. And I think this is the technique that we were using in the early 2000s when we just had a Class C limited address to the outside world. Using the overload keyword then means that we're not limited to the first 14 lucky employees, as many employees as the router can handle, thousands of employees. With 14 addresses, you can handle many thousands of employees, no problem. So in this case, PC1 and PC2 send packets to server 1 and server 2 in the outside world. Number 2, when it hits the R2 router, he'll do the translation. It'll be packeted towards server 1. PC2s will be forwarded towards packet server number 2. The NAT translation table then shows both devices. He'll modify port numbers if required. And then when it reaches the outside world, it'll come back, and the NAT service on R2 will change the outside global addresses of what he thought my PC1 and PC2 were back into the actual private inside highly protected 192.168 address that actually was, so that it survives the thrips through my routers and switches, and it'll show up at that employee's device. Okay, we can verify this, show IP NAT translations, and we can see PCA 10.10 and PC has gone to the outside world, it's come back, and it's been translated. And PCB 11.10 on the other network, he was translated to the outside world, and he came back, and it works just fine. Verify again with show IP NAT statistics. We can see the NAT pool. We can see the number of hits. In this case, we had 4 hits, 2 going out, 2 coming back in, and we didn't have any misses or problems. Okay, there was a NAT 64 that was developed. Why in the world for IP version 6, since we got 1 million Google addresses, would you need that? That makes NAT unnecessary. However, as a workaround tool, as something to be an interim tool, that it did actually develop a NAT 64 tool, so you can translate back and forth. What if you weren't a San Francisco firm, progressive, and you are using IP version 6, you're a company in Lincoln, Nebraska or something, and you're only using IPv4? Yet you need to communicate with that San Francisco company, which has totally dropped IP version 4, they only use an IP version 6. So there is a translation feature that allows IP version 4 packets to talk to IP version 6 packets in case this is needed. This is a deprecated thing. You really shouldn't use it. You should, at least your company should implement. Go ahead and use your old lousy legacy IP version 4 for now, and also implement dual stack IP version 6 so that in the future you can move to IP version 6 and get rid of your IP version 4. So NAT for IP version 6 it's really not the same as NAT for IP version 4. It's really a way of translating an IP version 4 packet to an IP version 6 packet. So on the upper right-hand corner, the IP version 4 host can send packets to an IP version 6 only network, and it's a temporary thing. You shouldn't use it as a long-term strategy. Okay, I'm old. I've been in the network business a long time. I'm an old network boy. So in the 80s and the 90s, we had Novell networks. We used IPX protocol instead of IP. It's IPX and SPX is kind of similar to IP and TCP in the same sense that Portuguese is kind of similar to Spanish. They're not quite the same, but they do the same sort of a thing. So if we were using a ISP that only transmitted IP version 4 packets and we had Novell networks to connect, I was like this when I was at Harcourt. We have to use a translation feature to change, encapsulate the IPX Novell packet and an IP version 4 packet, send it through the IP version 4 network to the home office in Orlando, and then the router in Orlando would open up the IP version 4 packet and spit out the IPX packet, which could then go to the home office server, and we would be able to see this. So NAT for IPv6 is sort of like this, a way of coexisting until we can get in the future and do this stuff. Okay, I want to show you now I'm going to bring up the packet tracer program and talk about this option that we have of using the real numbers that will match the lab report exactly, so you don't have to think about translating G00 to G000 and so forth. So I'm going to share the application, packet tracer, and I'll have to stretch it on the screen here to make it look good. Let's see, can I make it a little bigger? Okay, that's about as big as it can go there. Okay, now, oh, can we see the mouse? Oh, good, the mouse is shown here. Oh, that's right, in Packet Tracer, we can see the mouse here, but when I bring up the console screen, you can't see it. That's no problem. All I'm going to do today is, oh, I forgot to show the other thing, the lab report. Let me do that for a second. Stop sharing this. I wanted to show the, did I minimize it? Oh yeah, if it's minimized, it can't be seen. Okay, so this is the configure NAT for IP version 4. That's the assigned lab for today. Oh, you know, guys, this is great here. We're gonna have a whole week next week of no assigned labs. And then we'll have a couple more toward the end of the semester. So in this topology, they're using, does it show? How about if I do this? Okay. So we're gonna have 2 switches, 2 host PCs, and 2 routers. And in order to preserve this G001, G000, I'm going to go into Packet Tracer and show you how you can use a different router. Hang on, here, I'm going to check attendance. Oh dear, I timed out on TCCD. Hang on just a second while I log back into the attendance sheet. And I'll correct this attendance report. Oh, okay, this is great. We can't even time out. Okay. So I'll go to attendance tracking. And today is the 2nd. And I was supposed to be able to put in that you have arrived for attendance. 1, 2, 3, 4, 5, 6, 7. 4, 5, 6, 7. Okay, that looks good. Okay, sorry for that little break there. Okay, so what I'm gonna do now is go to Packet Tracer. Stop sharing this. Again, share Packet Tracer. It should be the right size this time. Okay, I can still hear my echo in the machine. You guys should be able to hear me just fine. So normally I would have been saying use the 1941 router. Oh, here we go, mouse. Okay, the 1941 router is what we have in our classroom. The problem is it has G00, G01. So instead, I'm going to pull up the topology for the 4000 series routers. These are the current generation routers that have replaced the 1900 routers. The 1941 router has reached end of life. It's still being supported. So I'm going to go ahead and put 2 routers in this topology. I'll put a router here, router here, and I'll go ahead and label them as R1 and R2. And and you can't see my mouse in the pop-up here, but what I'm going to do is go to configuration. Oh, he's still booting. Oh, he's booting. Wait for him to finish booting. Okay, he's booting now. And I'm going to make him, I think he's router 2. Let's see if I did that backwards or not. Okay, he's router 2. Now I'll do the same thing for router 1. Do the config, make him router 1. And now they're router 2 and router 1, and the mouse is showing up okay. So now when we look at this router, for example, it's gigabit 000 and gigabit 001. So my suggestion is if you want to try this instead of the 1841 or 1941 router, you'll find that the command line structure in the lab exactly matches when you go into the CLI of your router and do it. You won't have to think in your head, translate G000, it's only G00, because if you type G000 on the 1941 router, he freaks out because it doesn't match up properly. Okay, and the rest of the lab, we're going to use the old switches. So I'll go to the switch icon, drag up a couple of switches, which are to the left of the routers. And I'll tag them as device is still booting. Okay, we'll wait for it to boot. There we go. These devices in Packet Tracer boot a lot faster than the real devices because they're not the real iOS, they're a simulation. So switch 1, and then switch 0, I'll change to be switch 2. And then we have a couple of PCs that we need. So we'll go to the PC tab and pull up our plain PCs. And then I'll set those to be, I'm at the PC on the right. So he's going to be, oh, they do PCB on the left and PCA on the right. Wow, they're hoping you're on your toes here and watching what you're doing. I'll make that one PCA. And we'll make this one PCB. Okay, now let me drag this up here and neaten up a little bit. This is so tiny. Can I make that slightly bigger? I'm supposed to be able to do that with Control I. There we go, now it's a little bit bigger. Okay, so I'm going to finish up this demonstration in today's session by making the Ethernet connections in here. And then you can step through the step-by-step procedure. I've left a few things blank, just so you have something to type in when you turn in your lab, and I'll give you some credit for labs. So I'm going to click on the lightning jack and bolt connection thing and choose a solid straight through Ethernet connection. And I'll connect PCB to, it says port 18. I'll connect PCA to port 6, the traditional ports of 6 and 18. I'll connect the two switches together via their port 1s. Sorry, it pops off the top of the screen there. Then I shall connect the switch. Oh, I labeled the switches incorrectly. Sorry, let me fix that. Let me see. Let me do this connection and I'll change the switch numbers. Port 5 to G001. And let me see. I made the switch labels incorrect, so let me fix that. Don't want to confuse anything here. So this is, I'll make it temporarily switch nothing because it doesn't allow the two switch numbers to match each other. They have to be unique. So what I call switch 2, switch is actually, switch 1 is actually switch 2. And what I call the other one, I'll change it back now so he's switch 1. Okay, now we sort of match the topology, and I'll make my last connection, which was choose my solid Ethernet cable and go between G000, the remaining Ethernet port, to G000 of router 2, and the connection is made, and now you can go into the, bring up the CLIs and do the configurations for this and complete this lab. I just want to mention one more thing, and that is before, when you go into the, let me see here, bring up, let's stop sharing this. And I want to share, give me my mouse back, please. I'm going to share the application window for my TCC Blackboard. So when you go into Blackboard Collaborate Ultra, like you did to join here, at the top of the screen, there's a thing called Course Room. I lock it before our class sessions start so that students don't try to go in there by mistake and think that they're going to hear anything. And I unlock it when the session is over. After I finish up here, I'm going to unlock the course room again. So you guys are free to go into the course room whenever you want to, and the microphones will work. You can open your microphone. You can talk back and forth to each other and collaborate with each other if you want to. I just lock it when we have the course on, so there's no confusion there. Okay, I actually did record this session today. So after that processing takes place between Blackboard and YouTube, I'll have that posted real soon now. So the recorded presentation will be available to anybody that didn't make it. I say I count 7 here, and I have 7 in attendance. 1, 2, 3, 4, 5, 6, 7. Okay. Okay, guys. So when we come together next time, we're going to cover a couple more modules, and they won't be in next week. We're going to cover several modules. There'll be no labs to do there. So thank you for coming today, and hope to see you again next week. See you soon. And I'm going to go ahead and lock my microphone now and start the processing of this